Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.
So this is about forces, isn't it? You know, we said that for your level, we can just talk about force as a pull or a push. And so this is forces and effect of forces. Let me zoom it in as much as possible so that we can write better. I'm here, so let's go forces and effects. Effects of forces. Please, you do not just hold on for me. I will tell you when to write. Okay? Forces and effects of forces. You know the effect of forces. Can you mention them? Effects, we have change in direction, change in direction,
change in speed,
because a force can move an object in a different direction. An object that was already moving in a particular direction, because of the application of a force, it can move in a different direction. B,
change in shape,
change in shape. C,
change in speed,
change in speed, because it can move faster or slower. A force can speed up an object or slow it down. Change in speed. These are basically the effects of a force. And you know the different types of forces. What are the types of forces? No, types.
push or pull.
Well, I'm not necessarily talking about examples. I told you about the two main categories, the two main classification of force. I'm not sure I mentioned it, but I thought I did. There is contact force. Contact force requires that there is a contact made. Can you give me examples of contact forces? You have friction, air resistance, tension, and what have you? You know, pressure is not a force. Pressure is actually force over area. So you have friction, tension, compression, and all that. Tension is a stretching force. You know that?
Yeah.
While compression is a squashing force.
Yeah.
All right. Contact, there has to be a physical contact between the objects. Then you have non-contact. Non-contact, as the name implies, you don't need to do non-contact force. What's another name for non-contact force? We call them field force. Non-contact force or field force. So what?
Field force.
Examples. You have gravitational force. Gravitational force. Radiation is not a force. Gravitational force, magnetic force, or you can talk about electromagnetic force, magnetic force, and electric force. Or you can group the two together as electromagnetic force. They are all called what?
Non-contact forces.
Non-contact forces. Okay, so we can talk about examples of forces. Have you mentioned some of them already? Examples of forces, can you mention anyone? What's friction?
The force that acts to oppose the motion of two objects that slide against each other.
Okay, so frictional force opposes the motion of two objects that are sliding against each other. So what direction does frictional force always act?
Backwards.
Well, you mean in the opposite direction to the motion. Frictional force opposes motion of two objects that are sliding against each other. Two objects that are sliding against each other. All right, that's frictional force, and it always acts in the opposite direction to the what? the motion.
Yes.
Because it opposes the motion, right?
Yes, sir.
Acts in the opposite direction to the motion of two objects that are sliding against each other. Now, air resistance is frictional force that acts in air. Do you know?
Yes. Yeah, resistance.
Air resistance is frictional force in air.
Yeah.
Frictional force in air. Another name for air resistance is drag. Do you know that?
Drag.
Okay, so let me just air resistance or drag.
So how come? Because it's dragging.
It opposes the motion of an object that is moving in air. So it's a drag. So air resistance, frictional force in air. So we can also talk about water resistance. So frictional force in air.
Water resistance.
By the way, to reduce air resistance, what should you do?
Increase the weight.
Are you sure?
No, increase the speed.
To reduce air resistance.
Reduce the cross-sectional area.
In fact, let's talk about it. To reduce air resistance.
Increase the cross-sectional area.
Did you say increase?
Reduce the cross-sectional area.
To reduce air resistance, you have to reduce the cross-sectional area. Isn't it?
Yes.
And what do we call that?
Streamline.
Streamlining, you have to reduce cross-sectional area. Reduce cross-sectional area. In other words, makes the stuff pointed so that it can glide easily through the air. It can easily glide through the air, isn't it?
Yeah.
That's called streamlining, like the way the bodies of aeroplanes and birds are naturally designed. So to reduce cross-sectional area what you call streamlining, right?
Yeah. So.
It's not just in air, even in water, like the ship. You know the way the body of the ship is designed with the point so that it can glide easily through water. Streamlining. Even the fish is naturally streamlined. So reduce cross-sectional area. What other way can you reduce air resistance? Reduce the speed. Reduce speed. Anyway, we'll talk about that. That's what we're looking at. Reduce speed. A reduced speed can also reduce air resistance. So we can talk about water resistance and so on. In fact, generally, any friction in a fluid is called viscosity or viscous force. What's a fluid? Liquid or gas. So viscous force is frictional force in fluid. Right? Frictional force in what? Frictional force in fluid. In a fluid. So air resistance is a viscous force. Water resistance is a viscous force because air resistance is a frictional force in air, isn't it?
Yes.
In fluid, which of course is liquid or gas. You have liquid or gas, that's a fluid. Okay, that's about viscous force generally. So just like I said, when the liquid is thicker, it will, the object thrown into the liquid will sink slower. That means there's a higher resistance. That's a higher viscous force. They're all about resistant frictional forces in the fluid. Okay, that's about that. We can look at generally the laws of motion. Do you remember them?
Yeah.
Inertia. The momentum, the action.
Okay, so let's look at the Newton's laws of motion. Newton's laws of motion. Laws of motion, where these laws can be valid at certain level at certain conditions for certain conditions, but there are certain conditions, especially at the micro level, that it may not be that valid, but that's beyond your scope until you get to particle physics at A levels. Some of these laws are no longer that valid at that point. Now, so you are just getting better and better. So the first law is about inertia. Well, inertia itself is resistance to motion. This is what inertia is about. If something is like this object on this table, it's going to resist my moving it. If it was also moving, it will also resist my stopping it. Let me say that again. I have an object placed stationary on the table. You know, I have to apply a force to move it.
Yes.
I have to do what? I have to apply a force to move it because it is going to resist the state it already is at the moment. So you need a force to change that state. So inertia is about resistance to motion or rest. Oh, something is at rest and it wants to remain at rest. So you need to apply a force to tell it, I don't want it to stay at rest. Move. Now, the object may also be moving and it may want to continue in that motion. So you need to also apply a force to resist that motion and stop it from moving. So inertia is a resistance to motion or to rest. Okay, so the first law is about inertia. This is why it's about inertia. About inertia. And of course, inertia is affected by the mass of the object. First law is about what?
Inertia.
Okay, inertia is affected by the mass. Inertia is resistance to, let me just talk about inertia. Inertia is resistance to what? Rests or uniform motion. Resistance to rest or uniform motion. Uniform motion is a motion at a constant speed. Let me explain. So resistance to rest or uniform motion is inertia. Resistance to rest or uniform motion, inertia. Now, this is the law. Do you remember? What's the first law? An object will remain in a state of rest or uniform motion. An object will remain in a state of rest or constant speed. Let me just say constant speed or constant velocity. Let me just say constant velocity, which we call uniform motion in a straight line.
Yes, sir.
In a straight line, unless what?
Unless there is an external
Resultant force.
yes that acts on it.
Unless there's an external resultant force.
That acts on it.
I need to explain what I mean. It's actually very easy. It's something we can easily relate to. If you leave this object here, it will continue to be here. That's why I told you that the first law is about inertia. It will continue to be here. It doesn't want to leave the position it is. Unless you have an external resultant force acting, it will stay in a state of rest. Also, if it was already moving in a constant speed, constant velocity, it will also continue to move in non-constant velocity forever, unless there is an external resultant force acting on it. This will get clearer as we continue. So let me just talk about it. The first law is about inertia, and inertia is resistance to rest. I say resistance to rest, or uniform motion, that's constant speed, or you can just simply say constant velocity. There's a reason why I have to specify velocity, because something can be moving at a constant speed, but not necessarily constant velocity. In fact, constant velocity, we mean constant speed in a straight line, but we'll talk about that. Okay, unless there's an extent. So an object will remain in a state. An object will remain in a state of rest or constant velocity, which is uniform motion in a straight line, unless there's an external resultant force on it, acting on it. So having said that, because we need to talk about the second law for you to understand. The second law
Is momentum.
The second law is about momentum. Because we are here to do momentum, I will just explain it in terms of acceleration and resultant force. The second law is about momentum. When we look at momentum in another lesson, you will understand better. Second law, are you ready for that? I said the second law is about what?
Momentum.
Okay, you do not know what momentum is yet, so we'll leave it at that. So it's about momentum.
Mass and acceleration.
Well, momentum is mass and velocity, so but let's leave it at that for now. Momentum is mass and velocity, but don't bother about it. You will see it in another lesson. Second law. Second law is widely applied in physics at this level. Widely applied. Second law is acceleration is directly proportional to the resultant force. Do you know?
Yes, sir.
So acceleration is directly proportional to the resultant force. What does that mean?
Like it's the same as the resultant.
Are you sure?
Like,
Please, can you tell me what this statement means? Acceleration is directly proportional to the resultant force. What does it mean? Explain quickly.
So the resultant force is equal to the acceleration of the object we assume after the resultant force acting.
I really don't think it is equal like that. But I think you are coming closer to it. What does it mean to say that something is directly proportional? We talked about something directly proportional in Hooke's law.
In the same way, like this one changes in this way, the same way.
You're getting closer. When? Say that again.
Like,
Please let him answer.
if the resultant force changes one way, the acceleration changes in that same way.
Okay, first of all, you are getting very close. Which one affects the other?
Resultant force and acceleration.
Okay, resultant force is what affects acceleration. So resultant force is the independent variable. Acceleration is the dependent variable. As resultant force affects acceleration. Acceleration depends on resultant force. So can you explain it in terms of what you just said?
Okay.
As
the resultant force changes,
Good.
the acceleration changes.
is that all? You said as the resultant force changes, acceleration changes. Is that all?
Same way.
Okay, what you're saying is as the resultant force changes, acceleration changes at the same rate.
Same way.
In other words, as the resultant force increases, acceleration also increases at the same rate. That at the same rate is very important. If it is not at the same rate, they are not directly proportional. Did you hear me?
Yeah.
As the resultant force increases, acceleration increases at the same rate. As the resultant force decreases, acceleration also decreases at the same rate. You know, that is the only time both of them will be directly proportional. Now, I told you when you are plotting a graph of one against the other, One is usually on the x-axis. By the way, this is the mathematical representation of that. F equal to ma.
So solution is E equals to mc squared.
We get that. That's about Einstein's equation. You do that at A levels. F is equal to ma. F is equal to ma. For what does F stand for?
Force.
Remember what we said there. What does F stand for? Say that again. F stands for resultant force. F is resultant force.
Why can't we just write RF instead of just writing it?
Okay, let's always remember that F stands for resultant force. What does A stand for?
Mass.
What does A stand for?
Acceleration.
Acceleration. A stand for what?
Acceleration.
Please pay attention. What does M stand for? What does M stand for?
Mass.
Mass. All of these quantities must be in SI unit. Force is in what?
Newton.
Force is in Newton. In Newton. And mass is in what?
Mass is in gram.
In kilogram, kg. While acceleration is in what? Meter per second squared. Yes, you need to. All right. Let's do a simple illustration. Are you ready for that? Are you ready?
Are you ready?
Are you ready?
Yeah.
Look at this. Oh yeah, look at this. Look at this, everyone. I have two graphs, or three actually. Three actually. Watch this, everybody. Watch this. Watch this. Watch this. I have this one. By the way, for something to be directly proportional to something, please pay attention. Please let me make this. Let me draw 4 graphs. Let me draw 4 graphs instead. I can zoom it in as. Let me even zoom it into 200% so that I can draw as many graphs as possible. Pay attention. This is where you need to be very, very careful because I'm getting deeper into this. So let's be careful so that we don't mix up stuff. This is the first graph. This is another one.
So bold.
This is another one. This is another one. You can tell me the ones that are directly proportional. I have usually, because force is the independent variable, it is placed on the x-axis. Acceleration in meter per second squared on the y-axis. But it can be placed differently. Yes, force can be on x-axis. I mean, the force can be on the y-axis, acceleration on the x-axis. But for the purpose of my illustration, I want to just do it like this way. Watch this. Watch this. Okay, let's see this one. Also force in Newton. Acceleration in meters per second squared. Let's see this. And let's see this one. Force in Newton. Acceleration in meter per second squared. Let's see this. 2 graphs. I Which one is actually showing us about something being directly proportional to the other? You see, that's why you don't just say as one increases, the other increases. Because that's also what's happening here. As force increases, acceleration is increasing, but not at the same rate. How is this one increasing? At an increasing rate. Do you know this is as force increases, acceleration is increasing at an increasing rate. So it's not at a constant rate. So it is not directly proportional. This one is as force increases, acceleration increases, but at a decreasing rate. Now, this The third one is as force increases, acceleration increases at a constant rate or at the same rate. So, by the way, beautiful. That means it is graph 3 that we can say acceleration is directly proportional to resultant force. For a quantity to be directly proportional to the other, two conditions must be satisfied for the graph. What are the two conditions?
The line must be straight line.
And it must pass through the origin.
So it must produce a straight line that passes through the origin. If it is a straight line that did not pass through the origin, are they directly proportional?
No.
No, sometimes they may ask you, state how you can tell that acceleration is directly proportional to resultant force by observing the graph. How can you show that acceleration is directly proportional to resultant force? What will you say? It's a straight line. It produces a straight line that passes through the origin. The two conditions must be stated. Okay, now I want you to see this. I need you to see this. This one is where I'm going to, and it's getting really interesting. Let's see this. Look at this. Let me make it easier. Let me make it easier before I do it the other way. F in Newton, acceleration in meter per second squared.
Sir, can you do like both things?
In what?
Can you you can change it?
How do you?
Like, force will be down.
Yes, that's what I just did.
Okay.
That's what I just did. Watch this. Watch this. Are you ready?
Yes, sir.
Watch this. Listen very attentively. See this. If I take the slope, you know I told you when you are drawing the slope, it should be as big as, the triangle should be as big as possible, isn't it?
Yes, sir.
The triangle should be what?
As big as possible.
You know, when you have a big triangle as big as possible, it means you have considered a larger result, so it's more reliable. If you draw a very small triangle, like a small triangle, you didn't consider a large result. So the bigger the triangle, the more reliable your result is. It should be as big as possible. And you know when you are drawing your graph, the line should be a line of best fit, is it not?
Yes.
Alright, so let's see. What will the slope give me? Slope will be what? Or slope or gradient, what will the slope give? Slope is equal to what? Slope or gradient is equal to what? What over what? Which is what over what? Rise over run. What's the rise? Force. What's the run? So the slope is F over what? F over A. And what's F over A? Let's look at it. Look at it here. Look at this. This is where it is important. You need to pay attention to it. Slope is rise over run. Slope is what again?
Rise over run.
Which is force over A. Force over acceleration. And what do you think force over acceleration is?
Mass.
Yes. That's correct. Make force over acceleration. You saw it the formula. F over A will give you mass. Did you see that?
Yes. Other way around.
So the slope is mass. Did you get that?
Yes, sir.
The slope is what? Mass. Did you get that?
Yes, sir.
The slope will give you mass. The slope will give you mass.
Oh my, really?
All right, let's see this. Let me plot it differently. Let me plot it differently. If you have acceleration in meter per second squared against force in Newton, and then you have this graph, like it will also produce this same kind of graph. If we take the slope, what are we going to get?
Mass.
Are you sure?
No.
You had better be careful.
Wait.
No, wait, no.
What will this slope give you now?
Sir, calm down. Let me
I am.
Acceleration.
This now is now acceleration plotted against
One over
force.
N. What you say?
Yeah,
One over N.
That's very intelligent of you.
Thank you, sir.
Because this gives, the slope gives, watch me, the slope gives rise. What's the rise? What's the rise?
Acceleration.
The rise is acceleration. What's the run? So the slope is, in this case, the slope is what? Acceleration over force. which gives 1 over m. That's inverse of m. Please pay attention. If F over A is mass, so A over F will be 1 over mass, isn't it? So this is 1 over mass. Is that understood? Now, this is the catch that I need you to pay attention to. Watch this.
Yes, sir.
Watch this. You had better watch this. You had better watch this. You had better watch this. Now, let me show you this. Look at this graph. Look at this graph. Watch me. Listen up. The blue line and the yellow line, which one has a bigger mass?
I think the blue line.
The blue line and the yellow line, which one has a bigger mass?
The yellow.
Why do you think the yellow has a bigger mass?
It's wider.
It's less steep.
Yeah.
What does a steepness give you? I hope you know steepness is slope.
Okay.
Steepness, tangent, gradient, slope, they are all talking about the same thing. Which one is steeper?
Blue.
The blue is steeper than the yellow.
Okay, so the mass of the blue is
So which one has a bigger mass?
blue.
The blue or the yellow?
Blue.
The blue has a bigger mass, isn't it?
Yeah.
Did you get it?
Yeah.
Why does the blue have a bigger mass?
But it's deeper.
And the steepness gives,
A larger.
the steepness is equal to what?
F over.
The, is equal to the slope. And the slope for this particular graph gives directly what? Mass. Listen up. The blue line is steeper, and the steepness or the slope, which is F over A, is mass. So since the blue line is steeper, it has a bigger mass. In other words, the blue line has higher steepness, so it has a bigger mass. Because this is the graph of force against acceleration, or resultant force against acceleration. The slope is directly mass. Now watch this. I'm going to draw another one. See another line I'm going to draw. This one is a green line. This yellow line and the green line, which one has a bigger slope? Oh, slope. I mean slope. Which one is steeper? Oh, it's not showing green. Oh, it's showing differently. Oh, I get it. It's showing differently at your end. No wonder it's showing differently at your end. Okay, this upper one. Let me see if I can use a different color. Let me use black. So that I can show you the way I want it to show.
Oh, that is black.
Is it showing black now? Yes. Okay, watch this. The black line and this yellow line, but I think I need to use a different color. Which other color can I use?
Black.
Let's
So you
use
need to
red.
update your colors.
Yes. Is it showing red? No. Okay, never mind. The red line, I think the best thing is to use. Just know that I'm using a different color. I don't want it to be a color that I have here. Okay, the upper one, which is actually green. Just know that this upper one is green, and this lower one, which is yellow. Which one has a higher slope? Obviously, the green one. Is it not? Obviously, what?
The green one.
But which one has a higher gradient? A higher slope is the green one. Which one has a higher mass?
The green one. The green one.
Which one has a higher mass?
The green one.
Why do you think somebody say green, somebody say yellow? Why do you think it is a yellow one?
Because.
Yeah, go ahead, I'm listening.
Well, you know, I don't really know how to explain.
So go ahead and explain it. Why do you think the green one has a bigger? You said the yellow one has a bigger mass than the green one. Why do you think so?
It's acceleration over force here.
Actually, that is correct. Because this graph is a graph of acceleration against force. It's like the reverse. So it is actually the yellow one that has a bigger mass, even though the green one has a bigger slope. Did you get that?
Yes.
Did you get that?
Yes.
Did you get that?
Yes, sir.
Okay, let me see if I can find a small space to write that. Let me see if I can find a small space to write that.
Okay. Sorry, why me?
Hold on, let me see. Are you listening?
Yes.
Pay attention. I said the force for which one? The green one, is it not? No, the force for the yellow one. The force for yellow is bigger than.
First for green.
Oh, I said force. I should have said mass now. Is it not?
Yes. Is that what it is?
The mass, please pay attention. The mass for the yellow, is that what we said?
Yes.
Is bigger than the mass for the green. Why?
Because it's the acceleration against force.
This is a graph of acceleration against force. It's bigger than the mass for the green. Can this really fit in here? Alright, how about this one? How about this one? This other one. What did you say about this other one?
Which one? F.
This one.
The blue one is steeper, so it has the higher mass.
A higher mass. The blue one is steeper, so it has a higher mass because it is force against acceleration, which gives directly mass.
Yeah.
So the mass, quickly, the mass of the blue one
Yeah.
is obviously bigger
Because it's steeper.
than the mass of the yellow one. I hope you can get the difference. You can get the difference? Okay. Now, listen up. Do you know that we can also plot force against mass?
Force against.
Yes,
Yeah.
So all these plus, what's before?
They are going to be important in what I'm going to explain to you now. Let's see this. Watch this. I'm going to show you where they find uses. If I plotted force against mass, yeah, force in Newton against mass in kilogram, and then of course we also get a straight line that passes through the origin, or whatever. If we get a line like this, or whichever way you go, what would the slope give? What would the slope give? Class, tell me, what would this slope give?
Acceleration.
Are you sure?
Yeah.
Okay, please listen up.
Because F over.
From F equal to MA, the slope is actually rise over run, isn't it?
Yeah.
Which is force over M. Force over M will give you what?
Acceleration.
It's acceleration. The slope is actually acceleration. And without even wasting time, if you have this, watch me, if you have this, and you have this, which one produces a bigger acceleration?
The yellow one.
The yellow one.
Yeah.
The yellow one produces a bigger acceleration. So the acceleration for the yellow one is bigger than the acceleration for the green one. Right? Do we agree? What about if it is plotted the other way around? If it is plotted the other way around, let's see. If it is plotted M against mass in kilogram, please, this mass must be, when you are solving this, take note of this. The mass must be in kilogram. It must be in SI units, which is kilogram. If you plotted mass against force in Newton, and then you get these two, you get this, and then you also get this. You get, let me use this. Which one has a big, by the way, what would the slope give?
1 over A.
Let's find the slope.
1 over A.
let me use a yellow line to draw the slope. Are you getting this?
Yes, sir.
You said the slope will give me what?
1/8.
Slope is rise over run. What's the rise? Mass over force. And mass over force will give me what?
1/8.
1 over acceleration. Which one has a bigger acceleration? The black, because it's the other way around. So acceleration for the black one is bigger than acceleration for the blue one. Do you agree with me?
Yes.
Alright, because it is plotted the other way around. Now there's something very, very important that we need to do now. Please listen up. I need your full attention. This is getting really, really, really important.
Okay, we can make a number of deductions from this second law, which says that acceleration is directly proportional to the resultant force, or F equal to ma. That's F stands for resultant force in Newton, m stands for mass in kilograms, a stands for acceleration in meter per second squared. So from F equal to ma, from F equal to ma, that's resultant force equal to mass times acceleration, which is the equation of the second law. We can see that when force is equal to 0, let me zoom it in a bit. If force is equal to 0, when force is equal to 0, it means that acceleration has to be equal to 0. Because if F is 0, the only explanation is that A is also equal to 0. Because only when mass multiplies by 0 that you will get 0 for the resultant force. So whenever the resultant force is equal to 0, acceleration will also be equal to 0. Let me just put it this way. When F is equal to 0, the resultant force must be also equal to 0. Or when F, which is resultant force, is equal to 0, acceleration must also be equal to 0. So when resultant force is equal to 0, it means that acceleration must be equal to 0. Must be equal to 0. So when resultant force is equal to 0, acceleration must be equal to 0. What's the implication? When resultant force is equal to 0, it means acceleration is 0, which means the object is moving at a constant velocity. Therefore, object is moving at a constant velocity or steady speed. Steady speed, because for acceleration to be equal to 0, it means the speed is steady, no acceleration. So 0 acceleration means 0 resultant force, or 0 resultant force means 0 acceleration. So when resultant force is equal to 0, acceleration is equal to 0. Or we can also say when acceleration is equal to 0, resultant force is equal to 0. Or when the object is moving at a constant velocity, there is no resultant force. Another way to put it is, another way to express this is, this is another way we can express it. When the object is moving at a constant speed, or when the object is moving at a constant velocity, when the object is moving at a constant velocity, in other words, when speed is steady, that's at a steady speed, on a straight line, that's for a steady speed on a straight line. for a steady speed on a straight line, it means that there is no resultant force. There is no resultant force. Why? Once there is no acceleration, the object is moving at a constant speed or steady speed in a straight line. In a straight line. And for that to happen, from what we have derived, for A to be 0, then resultant force must be equal to 0. So there's no resultant force. So these two statements are saying the same thing. When resultant force is equal to 0, acceleration is equal to 0. Therefore, object is moving at a constant speed or steady speed in a straight line. Or we can say when the object is moving at a constant speed, that's a steady speed, or moving at a constant velocity or steady speed in a straight line, there is no resultant force. From here, we can also see that if resultant force decreases, gets smaller, it means acceleration will also get smaller, because if mass is constant, the only explanation is that acceleration is getting smaller. So when resultant force is decreasing for a constant mass, acceleration will also have to decrease. I can also say that. It can also be shown that we can also see that when resultant force decreases, okay, can I just say, it can also be seen that for a constant mass, that's when mass is not changing. For a constant mass, when resultant force decreases, for a constant mass, when resultant force decreases, then acceleration also decreases. That's not difficult to understand, because if the resultant force F is getting smaller, when mass is constant, it means acceleration has to also get smaller. So that mass times that acceleration will give you a smaller value. So we have deduced a number of points. Let me zoom out so that we can see all of them together. We have deduced that from F equal to ma, when resultant force, which is F, is 0, the only reason is, or the only explanation is, acceleration must also be equal to 0. So that mass times the acceleration will give you that 0, which is the resultant force. So when F is equal to 0, A is equal to 0. Or in other words, when resultant force is equal to 0, acceleration is equal to 0. Therefore, object is moving at a constant speed or steady speed in a straight line. So another way to express it is, when the object is moving at a constant speed, that is at a steady speed in a straight line, steady speed in a straight line, it means the resultant force is 0. In other words, there is no resultant force. And we can also see that for a constant mass, when mass does not change, when resultant force decreases, then acceleration also decreases. The only other time is when mass decreases for a constant force, resultant force, acceleration will also has to increase. So what I'm saying is, if mass decreases for a constant force, it means acceleration has to get bigger, so that when you multiply by the mass, we still get the same value. I don't need to say that, but that we can easily deduce. If you have a constant value of resultant force, and the mass is getting smaller, for any reason the mass is getting smaller, it means acceleration has to get bigger, so that when you multiply the mass by that acceleration, that smaller mass has to have a bigger acceleration so that the two will multiply and still give you the same value of resultant force. In other words, resultant force is constant. All of these things we have talked about can be explained by the first law, that an object will continue in its state of rest or constant velocity when there is no resultant force acting. Unless there is a resultant force acting, the object will continue in its state of rest or constant velocity. So once resultant force is now acting, there must be an acceleration. There must be an acceleration, which means it will no longer be moving at a constant speed. So an object will remain in a state of rest or constant velocity if there is no resultant force. Now, if there is a resultant force, it cannot move at a constant velocity. I think I can just state that. So I can also add that if there is a resultant force, let me zoom it to 100%. If there is an external or a resultant force, if there is a resultant force, there is a resultant force on an object, the object cannot move at a constant rate, cannot move at a constant velocity, because there must be an acceleration. So once we have a resultant force, there has to be an acceleration. Based on this formula, once there is a resultant force, there must be an acceleration. If a resultant force has a value not equal to 0, there must be an acceleration. Because mass has to multiply with something which must not be 0 to obtain a value which is not 0. So if there is a resultant force, there must be acceleration. So the object cannot move at a constant speed. I can also say that if the resultant force is negative, if you have a negative resultant force, then there has to be a negative acceleration, which means deceleration. So the object is slowing down. Let me add that with a black line. If the resultant force is negative, then the acceleration has to be negative. Which means deceleration. Which is deceleration. So when the resultant force is negative, the acceleration must be negative, which means deceleration. Because from here, for this to be negative, that means A has to be negative, because mass cannot be negative. For this to be minus something, it has to be A that will be minus something, because whatever the mass is, mass cannot be negative, mass is always positive. The mass times minus A will now give you minus F. So when there's a negative resultant force, there's a negative acceleration, which means deceleration. Alright, so all of these we must take note of. There are 4 points. These in yellow, in green, in yellow, in blue, in green, in red, and in black. That's 5.1, 2, 3, 4, 5.
For the second law, for Newton's second law, we already established that the second law is about momentum. And the full statement of the second law is the rate of change of momentum is directly proportional to the applied force. So second law definition or statement of the second law in terms of momentum. Newton's second law of motion in terms of momentum. In terms of momentum, it says the rate of change of momentum is directly proportional to the resultant force. And it takes place in the direction of the resultant force. So the rate of change of momentum is directly proportional to the resultant force, and it takes place in the direction of the resultant force. Momentum itself is mass times velocity. A simple illustration could be this. If an object of mass m starts with an initial velocity u, and later this same object of the same mass changes to another velocity v, same mass m. The momentum or initial momentum is mu. The final momentum is mv. Change in momentum will be equal to, change in momentum is mv minus mu, because change is about the difference. Remember, the initial momentum is mu, the final momentum is mv. Let me call this initial momentum. While this one is final momentum. I think we can write it better so that it will come out clearer. This first one is initial momentum. Let's clean this and put it in the other way. So this first one is initial momentum. While this second one is final momentum. So initial momentum mu, final momentum mv, change in momentum, the difference, which is mv minus mu. That's for change in momentum. Now, rate of change of momentum. Rate of change of momentum is equal to, when we talk about rate, we measure the quantity with respect to time. So mv minus mu divided by time, or m, if we factorize, we have v minus u all over time. Factorizing out m, if m comes out, we have v minus u over t, and we know that v minus u over t is acceleration. V minus u over t is acceleration. So this whole thing becomes ma, and from the initial way we studied it, ma is equal to force. Since ma is equal to force, it means force is the rate of change of momentum. You know, so this is equal to force based from our initial explanation. Ma is force, so that force is the rate of change of momentum. Is rate of change of momentum, and v minus mu over t. So force is proportional to the rate of change of momentum. That's what we have written here. Or the rate of change of momentum is directly proportional to the resultant force. Remember, this F stands for resultant force. Okay.
Now, we can talk about the third law. This is Newton's first law. This is Newton's second law. Remember, the first law is about inertia. The second law is about momentum, which we discuss in higher level or later. And the third law is about action and reaction. So I can note it down here, or it can even be noted down here. So I will just zoom in. Let me zoom into 200%. So third law, Newton's third law. This should be C. Third law. Third law is about action and reaction. Action and reaction force. This third law is basically saying that if there is a force acting on an object, there will also be an equal force, but in the opposite direction from the object. The simple way of putting it is, when a force acts at a point at an object, or act on an object, or even from an object, there will be an equal but opposite force acting as well. Usually, to say this, we say for every force there's an equal and opposite reaction force. The force that acted is an action force. The reaction force, which is opposite to it but equal, is the reaction force. So when a force acts on an object, there will be an equal but opposite force acting on the same object. or at the same time. For every force, there's an equal and opposite reaction. It's just like if you have this object resting on a table. This is the object resting on this surface. Is the surface this object is resting. Now, a force which of course is the weight of the object is acting downward. That's the weight. Weight always acts vertically downward. For this object to be balanced, there has to be an equal, but this time around opposite force which acts from the surface, which we call normal reaction or reaction force. So the force of the object, the force which is the weight of the object which acts downward, produces a normal reaction from that same surface which acts upward, so that the object can stay in equilibrium. If the weight is 50 Newton, the normal reaction will be equal to 50 Newton. For every force, there's an equal and opposite reaction. That's Newton's third law. It's about action and reaction. For every force, like the weight, there's an equal and opposite reaction. Now, this principle is what is applied in the motion of jet-driven planes. For instance, or aircraft like a rocket. For a rocket, all we need is to produce a propelling force on a rocket. Let me use this to represent the rocket. At the tail of a rocket, there are exhaust gases that are being ejected at very high speed. The force of these exhaust gases, these are gases, gas emitted and moving at a high speed. So the force of this gas, which is being emitted and moving at a high speed, going in the opposite in this direction, for instance, downward, we produce an equal, but this time around opposite. Let me zoom it in a bit, zoom it out a bit so that we can see it better. The force of this gas, which is emitted and acting downward, we produce an equal but opposite reaction force, which pushes the rocket up. This is the reaction force. Reaction force that propels the rocket. The rocket in the opposite direction, upwards if you like. So this reaction force will propel the rocket upwards as gases are burned and emitted at the other end in the opposite direction. If you want this rocket to move up or move upwards, we need to emit these gases. The force of the moving gas, which acts in this direction, or the emitted gas which acts in this direction, the force of this emitted gas which acts in this direction downwards, we produce an equal but opposite reaction force that will be pushing the rocket in the opposite direction, propelling it in that opposite direction. That's where we can find this in display. Okay? Straight to centripetal force and centripetal acceleration. And centripetal acceleration. whenever an object is negotiating a circular path, there must be a force that will be required to make that happen. So what I'm saying is, if an object is trying to move around a circle, like the first example we gave, an object trying to move from P1 to P2, it can only happen if there's a force. And the reason is this: if this object is moving anti-clockwise as shown, at every point we can draw a tangent to show the speed at that point. That's the speed at P1. Also the speed at this point is this green one. Now assuming it is moving with a speed of 10 meters per second, so at P1 is 10 meters per second, at P2 is also 10 meters per second, same speed. But you can see that direction is changing every time. So even though the speed is constant, the velocity is not constant. So we can conclude that an object that moves in a circular path has a constant speed, but a constantly changing velocity because of the change in direction. So I will just note that an object that moves in a circular path moves at a constantly changing velocity. Right, so it's a constantly changing velocity, although the speed remains constant. The speed remains constant. Why can we conclude that? This is because the direction is constantly changing. And if you can recall, velocity is a vector quantity. Direction is constantly changing. Recall that unlike speed, velocity is a vector quantity, so direction is important. So once there's a change in direction, it has a different value entirely. Recall that unlike speed, velocity is a vector quantity. Which includes both magnitude, which is size, and direction. Alright, so very quickly, so that we can round off. Velocity is changing. Velocity is changing. And when velocity changes in a given time, that's acceleration. Remember acceleration A. So we can also recall that A is time rate of change of velocity. Rate of change of velocity with time. So because the velocity is changing with time, there's an acceleration. Therefore we can conclude that there's an acceleration. Therefore there's an acceleration. As velocity changes in a given time, there's an acceleration. Now, from Newton's second law, the popular law we know, from F equal to ma, if there's an acceleration, there must be a resultant force. By the way, F stands for
resultant force. F is resultant force. A is acceleration. And of course, M stands for mass. So if there is an acceleration, there must be a resultant force. That means the object has has a resultant force acting on it. So we can say that as there is an acceleration due to the changing velocity, there must be a force. There must be a resultant force. And resultant force acting on the objects, on the object that is moving in a circular path. In a circular path. Now this resultant force is directed towards the center, and that's what we call the centripetal force. This resultant force is directed towards the center, is directed towards the center of the circular path. And the resultant force is called centripetal acceleration. And the resultant force, or this resultant force, is called centripetal force. The centripetal force. So for centripetal force, the direction of the centripetal force is towards the center of the circular path. It's always towards the center of the circular path. So this blue arrow, which is towards the center, the direction is towards the center of the circular path, or towards O, is a centripetal force. Now the velocity, the direction of the velocity and the direction of the centripetal force, we make angle 90 degrees between them. So this angle between the blue line, which is the direction of the centripetal force, and the yellow line, which is the direction of the velocity, the angle between them is 90 degrees. So the angle between the velocity and the centripetal force is 90 degrees. So this velocity is at a tangent to the circular path. We call it tangential velocity. Okay. Now we can see some of the instances where you have the centripetal force at work. For instance, when a planet is moving around the sun, it is as a result of the centripetal force between the planet and the sun. For instance, if this is a planet moving around the sun is at the center of the circular path, and the planet is moving around it, there's a centripetal force that keeps the planet in that circular path. Without the centripetal force, the planet cannot move around the circular path. So if the sun is at the center and the planet, for instance the Earth, is moving around the sun, there's a centripetal force acting between the Earth and the sun, and the direction of that centripetal force is towards the sun, from the planet, for instance the Earth, to the sun. So it is what helps the planet to move around the sun. And what produces that centripetal force is the gravitational force of the Earth from the sun. In other words, the pull of the sun on the Earth. The gravitational force between the Earth and the sun is what provides that centripetal force. So the force that keeps a planet in an orbit around the sun, or that keeps a satellite in an orbit around the planet, is an example of a centripetal force. Now, if we are talking about a satellite like the moon, which is the natural satellite of the Earth, you know the moon moves around the Earth, for instance, or an artificial satellite moves around the Earth. In this case, the Earth will be at the center and the moon is moving around it. So it is also the centripetal force that helps the moon to move around the Earth. And that centripetal force is provided by the gravitational pull between the moon and the Earth. And that centripetal force is towards the center of this circle, which is in this case center towards the Earth. So there's a gravitational pull between the satellite, e.g. moon, and the Earth, which is towards the center or towards the Earth, that keeps the moon in an orbit around the Earth. Now, I said this centripetal force is provided by the weight or the gravitational force of the revolving smaller object. If it is this Earth that is moving around the sun, that is a planet that is moving around the sun, it is a gravitational pull from the sun on that planet, which is a smaller object, towards the sun, that provides a centripetal force. If it is a satellite that is moving around a planet, like the moon moving around the Earth, it is the gravitational pull of the Earth on that satellite. So the smaller object is the satellite. The gravitational pull of the Earth on the satellite, which is towards the Earth, provides a centripetal force that helps the satellite to move around the Earth. Another example where we can find the centripetal force is the force that keeps an electron in an orbit around the nucleus. You know, the electron moves around the nucleus, it revolves around the nucleus of an atom, just like a satellite moves around a planet, or a planet moves around the sun. So an electron also moves around the nucleus. The nucleus of an atom is located at the center. The electron, which is at the orbit, is moving around it. So there's also a centripetal force that helps that keeps the electron in this circular motion around the nucleus. In this case, it is actually provided by what we call the electrostatic force. That centripetal force is provided by the electrostatic force of attraction between the nucleus and the electron. We will do that when you get to static electricity or nuclear physics. There's a force of attraction between the nucleus and the electron. That force of attraction between the nucleus and electron keeps the electron in an orbit around the nucleus, as the electron is orbiting around the nucleus, which is at the center of the atom. So that's also where we can find an example of a centripetal force, and many more. You can also find it when a car, for instance, is negotiating a circular track. When a car is trying to move around a circular track, a car that is moving around a circular track, just like a car, this is a car trying to move around a circular track like this. A car moving around a circular track, there's also a centripetal force. Now that centripetal force for a car that is trying to move around a circular track is provided by the frictional force between the tires and the road. So a car that is moving around a circular track also has to have a centripetal force, which must act towards the center of the circle, or towards the center of the bend, the circular bend. And that centripetal force, what provides it is the frictional force.
between the tires and the road, the tires of the car and the road. It also provides the centripetal force needed for the car to move around the circular track. These are some of the examples of centripetal force in action. So, that's that. Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to two main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2 34808 509 5144 to learn more and get started today.